Chapter 4 is about heat, temperature, and atmospheric circulation. And our driving question is, what are the causes and consequences of heat transfer within the Earth-atmosphere system? Let's start off by distinguishing between temperature and heat. Temperature is proportional to the kinetic energy of molecules. So here I've got two gas samples contained in a chamber, and you can see the molecules are moving rather slowly here, therefore the kinetic energy is low. Once I apply some heat to the sample, the molecules move faster. There's more kinetic energy, and therefore there will be greater temperature in this gas chamber. So the faster molecules move, the greater their kinetic energy and the greater the temperature. Temperature can be measured. Heat, on the other hand, is the transfer of energy. Nature does not like it when things are ordered. So in the sense of temperature, if there are high temperatures in one place and low temperatures in another, nature doesn't like that. So it wants to transfer some of the heat, it wants to transfer some of the energy from the high areas to the lower areas in temperature. And that transfer of heat, that transfer of energy, is what we call heat. Temperature can be measured in a number of different scales. The ones we're most familiar with are Fahrenheit and Celsius. Fahrenheit, like Celsius, is based on the freezing point of water and the boiling point of water. In the Fahrenheit scale, the freezing point is called 32 degrees and the boiling point is 212 degrees. Celsius is metric, and things are base 10 in the metric system, so we use those 2 points to determine our 0 and 100 values. 0 is the freezing point and 100 is the boiling point. A third scale for measuring temperature is called Kelvin. Notice that Kelvin does not have the degrees symbol on it. We just call it Kelvin. And it is based on absolute zero. Absolute zero is the temperature at which all molecular motion ceases, and an object would emit no electromagnetic radiation. So that point happens at 0 K. And if we want to compare the other places that we looked at here, the freezing point of water is 273 K, and the boiling point is 373 K. Here you see different formulae for converting from all these different scales to the others. So if you're starting with Celsius and you want to convert to Fahrenheit, you would use this formula. Vice versa here. If I start with Fahrenheit and want Celsius, I would use this one. If I start with Fahrenheit and want Kelvin, I use this one. And if I start with Celsius and go to Kelvin, I use this one. Air temperature is measured with a thermometer, and the classic type of thermometer is liquid and gas. So some liquid, either mercury or alcohol. If it's alcohol, it's usually been colored red, like you see in this picture here. Mercury is the silver color it naturally is. It's confined in a glass chamber, and as the air temperature heats up, we have the liquid respond by expanding, and since there's nowhere for it to go, it just rises. And we put a scale showing the degrees Fahrenheit or Celsius or whatever temperature scale we're using, and we can read the temperature off of there pretty easily. We also have bimetallic thermometers, which use two different types of metal that have different expansion and contraction rates and can cause a dial to move, like you see in this type of thermometer. Electrical resistance thermometers are thermocouples. These are what are typically in thermostats in your house or in radiosondes that go up into the atmosphere to record temperature and so on. A thermograph, which we don't see a picture of here, is similar to the device you may see that measures the Richter scale. It's got a piece of paper inside and there's a needle that records the temperature throughout time. Whatever the method of observing temperature, you want to be aware of the accuracy of the device and its response time. How quickly does it respond to changes in temperature? For outdoor locations, it's important to make sure the device is properly located. It has to be far from a forest or vegetation. It has to be over a natural material, not over blacktop or some other man-made surface. And it has to be ventilated. If you had a thermometer just out in the sun, like anything in the sun, it's going to heat up more than what the air temperature would say. So we put a ventilation shield on it to prevent the sun from shining directly on the thermometer and also protect it from other weather. Temperature gradient is the change in temperature over distance. So here we have location in the northern Midwestern United States. And I have isolines that are lines of equal temperature called isotherms, and they're drawn at 5 degrees Celsius intervals. So I can see that it's cooler up here in the north and warmer in the south, which is what typically happens. Remember, nature doesn't like this order of cold temperatures and warm temperatures, and so nature wants to mix it all together. So heat flows in response to a temperature gradient. Heat will flow from warm areas to cool areas. And here they're showing movement from cool areas to warm areas, which can happen for different purposes. But typically when nature is trying to distribute these differences, it goes from high to low, whether it's pressure or temperature or whatever the case. Things move from where there's more to where there's less. The second law of thermodynamics basically states that nature doesn't like to have this kind of order. So nature likes to mix things up. Heat can be transferred in one of three ways: radiation, convection, or conduction. Radiation is the transfer of energy in a vacuum. We don't need a medium to transfer radiation. Think of the sun transmitting its energy to the earth through space. In this example, we have a campfire, which emits its heat through radiation. We also have conduction, which is the transfer of energy in a solid. So a solid, you can think of the molecules are tightly packed. And conduction is literally the transfer of heat molecule by molecule by molecule. So the example in our picture here is the pan that holds the water. The pan itself is made of metal. The molecules that make up the metal are tightly packed, and as they warm up via radiation, the bottom layer of molecules heats, it warms the next layer, and so on. That's why we have plastic handles or wooden handles on our pans, because metal would get too hot too quick to be able to touch. So we conduct energy through conduction in this way, or transfer energy through conduction. Finally, convection is the transfer of energy in a liquid, a fluid, I should say. So in this case, the pan is full of water, and the bottom part of the pan has warmed through conduction, and then the water that's in there warms in response to being close to that metal, and then as it warms, it rises up, and it transfers the heat up to the top where it's cooler, and the cooler water sinks, and we get these convective currents, these vertical currents that transfer heat. The same thing happens in our atmosphere. This slide shows conduction, molecule by molecule, passing the heat from one molecule to the next. And we see that some materials are better conductors than others, which means they more efficiently transfer the heat. So copper is a very good conductor. It's why we have copper wires, copper tubing, that make up our different systems here, electrical systems and whatnot. On the other hand, we have air, which is a very poor conductor. Convection is the movement through a liquid, and we can think of the Earth's atmosphere as a liquid. It's made up of a lot of water vapor and other gases that behave like liquids. And so what happens is the sun, through radiation, heats the ground, and the ground heats through conduction, so molecule by molecule by molecule. The ground gets warmer, a little bit deeper, depending on how hot it is. And then once the ground has warmed up, it warms the air that comes into contact with it, and then the air rises up, transfers that warm air to the upper atmosphere, upper part of the troposphere, and then the cooler air that's in that higher parts of the atmosphere sinks down. So we get these convective currents that transfer energy. Now, conduction happens very quickly, but convection is more efficient. So conduction can heat something up very quickly, depending on how good of a conductor it is, and then cool off very quickly. Whereas convection may happen a little bit slower, but once the heat has been distributed throughout the atmosphere or through some convective medium, it's going to stay warmer longer. It's going to be much slower to lose that heat than something that was heated by conduction. The specific heat of an object is the amount of heat required to raise 1 gram of a substance by 1 Celsius degree. So for example, water has a specific heat of 1, and you can see different materials have different specific heat values. So going down to copper and silver and gold, things that are good conductors, they have low specific heat, which means that they respond very quickly to changes in temperature. Whereas something with a higher specific heat is going to be more resistant to temperature changes. So a good example of this is water at the beach. If you go to the beach on a hot summer day and you're walking along the water barefoot, you'll notice that the sand is very hot. It's been heated by conduction and it gets hot quickly. Whereas the water may feel cool because it heats much more slowly. At nighttime, however, when the sun has set and the temperatures have cooled off, the sand is now cooler. And you may notice that the temperature of the water feels warmer compared to the air temperature or the temperature of the sand. This is again because water is more resistant to temperature changes. Once something heats up by convection, it is going to stay warmer longer. It won't lose its heat as quickly. Here is a graph that shows the difference between maritime and continental climates. Maritime climates are those near water, near the ocean. Continental climates are those that are landlocked. San Francisco and St. Louis share the same latitude, so they receive the same amounts of incoming solar radiation. You can see for St. Louis, the temperature as we go throughout the year has quite a lot of variation. It gets hotter in the summer and much cooler in the winter. So there's a huge variation because it's a continental climate. It's responding to the fact that the ground heats up through conduction. It gets hotter in the summer versus in the winter when it cools off. Whereas San Francisco stays relatively moderate here. The peaks are not so high and the lows are not so low. That's because of the calming influence or the moderating influence of the water of this maritime climate. The water's slow to warm up, but when it does, it holds its water and it has a moderating effect on the locations that are by the water. Here we'll look at the energy that's coming into the Earth atmosphere system, starting with solar radiation. We've already seen this in Chapter 3, but of 100% of the incoming solar radiation, some of it, and you see these values in percentages here, is returned to space through reflection or backscattering. Some of it, however, is absorbed by the atmosphere, the different gases and constituents of the atmosphere, and some of it, 49% of it, makes its way down to the Earth's surface where it's absorbed and can heat the Earth's surface. Once the Earth's surface is heated, it begins to emit its own energy in infrared spectrum, long-wave energy. So the energy that's emitted by the Earth, some of it is absorbed by the atmosphere. In fact, the bulk of it is absorbed by the atmosphere, by the greenhouse gases. They warm up and send more heat back down to the Earth's surface. Some of the energy is let go. It is emitted to space. That's from the Earth itself. And then some of the energy from the atmosphere in the form of clouds or some of the gases that make up the atmosphere also emit some infrared energy to space. And then you see here we have the sensible heat flux and the latent heat flux. We'll talk about these in a moment, but before we get there, let's look at our net shortwave energy input. So our net shortwave energy is going to be the amount of incoming solar radiation minus the amount of outgoing solar radiation. So how much do we get minus how much do we lose? The amount is the leftover net shortwave energy. We can do the same thing for long-wave energy. How much is coming in to the Earth atmosphere system and how much are we losing to space? The leftover is available to us as energy that we can do things with. So when we look at the energy budget for the Earth, the amount of energy available, we're looking at the net amount of shortwave energy plus the net amount of long-wave energy. And this energy is available to do two things. It can heat the atmosphere, this is what we call sensible heat, or it can cause a phase change in water, what we call latent heat. And we'll see in a moment a graph that shows latent heat, but basically we have water that exists in three states on Earth: ice, liquid, and vapor. And as water moves from one state to another, it either requires energy in that process or it gives off energy in that process. So you see here the different processes that require energy. So for ice to melt into a liquid, it requires energy. For liquid to evaporate, it requires energy. And then if we have a deficit of energy in our net available energy, have a deficit of sensible heat, and so things cool off. The phase change in water can still happen because going in these directions from liquid, say, to ice for freezing, it gives off latent heat. So for vapor to become a liquid through the process of condensation gives off latent heat, and so on. Sensible heat is heat we can feel, we can sense, and it heats up the atmosphere through convectional currents, and we can combine that with some moisture to create cloud growth, as we'll talk about in a future chapter. We get cumulus clouds, fair weather clouds in this kind of case when we have updrafts with moisture in the air. If the process continues, those cumulus clouds can develop into cumulonimbus clouds and create severe weather. So latent heating here, we see the three states of water, solid, liquid, and vapor. And as we go in this direction, move from a state from solid or liquid to vapor, we're moving from left to right in this graph, it requires energy. So the latent heat, it needs latent heat, so it's absorbed from the environment. So some of that energy that's available has to go towards making this phase change. So if it's been winter and it's suddenly warm and the snow is starting to melt, it requires energy for that to happen. Or if it's a hot day and the lake provides a lot of water for evaporation, it takes energy for that water to evaporate. Conversely, if we go in the other direction, we are giving off energy to the environment. So to go from vapor to condensation, or vapor to liquid, condensation happens with a drop in temperature, so we're giving off heat to the atmosphere, and similarly from liquid to solid. Here we can look at the different use of energy for two different locations. Yuma, Arizona, which is very dry, and Madison, Wisconsin, which is very wet. So what we have here is our net radiation absorbed in red. So we can see all the radiation that's absorbed. And then the blue line is the sensible heat. So how much of that energy is going towards heating the atmosphere? And you can see in Yuma, it's most of it. Compared to the green line, which is the latent heat, it's minimal. There's not much water in Yuma, so there's not much water to enact a phase change. So most of the available energy goes towards heating the atmosphere, and it gets very hot and humid in Yuma. And then the black line is storage, how much energy is being stored. And you can see that's pretty negligible, which is typically the case depending on the surface materials. But for natural materials, it's pretty negligible. For Madison, Wisconsin, it's further north, and it's also a very wet, moist environment. There's a lot of lakes, it's green, and you see of all the available incoming solar radiation, most of the available energy is going towards causing a phase change in water. And not so much of it is going towards heating the atmosphere. And the storage profile, you can see it's a little bit different than for Yuma, but still very negligible. If we look at what's happening on a global level, here we have the solid line represents the absorbed solar radiation, so how much of it is absorbed. And we have our x-axis is latitude, our y-axis is some measure of energy, watts per square meter, which is how we measure radiation receipts and energy levels that we receive through solar and terrestrial radiation. And we have the north hemisphere on the left and the south hemisphere on the right. And we can see that most of the solar radiation happens around the tropical area, which we know is to be the case. And how much of it gets absorbed, you can see here in the solid line. There's a little dip here in the northern hemisphere tropical areas. There's not one in the southern hemisphere. Why do you think that might be? Something to investigate. And you see what happens as we move poleward. There's less solar radiation absorbed because there's less solar radiation received. The dashed line shows the emitted infrared radiation. So once the Earth is heated up, it emits its own long-wave radiation or infrared radiation, and we can see that it's a little bit more around the poles than around the equator than it is around the poles. The pink areas are surplus, so where we have energy to use, and the blue areas are deficits, where we have no energy to use. Things are cooling off. So hotter areas, cooler areas. Remember, nature doesn't like these orderly ways of doing things in terms of temperature or anything really. Nature likes to distribute. So in this case, there's a transfer of heat from the equator to the poles that happens on a regular basis on the Earth. And that heat is transferred either by air masses, by storms, or by ocean circulation. Air masses, as we mentioned and we'll talk more about later in this course, are masses of air that pick up characteristics of their underlying surface. So near the tropics, we're going to have hot, moist air masses. And near the poles, we're going to have dry, cold air masses. And we have dynamic atmosphere and frontal boundaries that represent the movement of these different air masses transporting heat. Storms, hurricanes, for example, form in the tropical areas in the summertime, towards the end of the summer season and early fall when everything's heated up. And it's a way to transfer some of that energy from the tropics northward or southward, depending on which way the hurricane is going. And then finally, ocean currents also transfer heat. And you can see here the Gulf Stream and how this looks. We've got warmer waters around the tropical areas, cooler waters as we move northward in this case, and the jet stream that is causing this nice distribution of heat through the oceans. Here's the same slide we saw before with advection. This is a new term. Advection is the horizontal movement of air. Convection was the vertical movement. Advection is the horizontal movement. So again, we've got our temperature gradient, and we can have cold air advection, which means cold air blowing into where it's warmer, or warm air advection, air moving from warmer areas to cooler areas. Nature wants to move things from hotter temperatures to lower ones, but the atmosphere is dynamic, so there's more going on than just that single principle. So sometimes we can have air moving in this direction as well as this direction, and we describe it as advection. Here's the variation of air temperature with latitude. We see that locations near the equator have a more constant temperature profile throughout the year than locations that move towards the pole. Here's a Canadian location. You can see the summer and winter temperature is quite extreme in its variation compared to the equator area. And then in between, a location in the US, Kansas City, we see a similar profile as the Canadian city, but with less variation between highs and lows throughout the year. This graph shows the relationship between maximum insolation and maximum temperature. And we have time of day across the x-axis with noon in the middle. We have the radiation flux. It doesn't have values, it's just a relative scale here telling us how much energy, and then over here how much temperature. The green line shows incoming solar radiation. So it's 0 at night, and then when the sun rises, the incoming solar radiation increases till about noon when it reaches its peak, and then decreases till sunset. The purple line shows the terrestrial radiation. So it responds to what's going on with incoming solar radiation. So you see at night the Earth has been cooling off and continues to cool off until sunrise, and then once we have incoming solar radiation, it heats the surface of the Earth, and then that heats the atmosphere, and the Earth is emitting its infrared energy in response to that dynamic. And then once the sun sets, things start to cool off, and it starts all over again. And then we have temperature in red, which you see mimics the infrared radiation. So it's decreasing at night. It reaches its minimum just at dawn. And then once the sun rises and things heat up, the temperature responds accordingly. Now notice the difference between the maximum insolation, which is at noon, and the maximum temperature, which happens around 2 p.m. or so. This is called the lag of the maximum, and it has to do with the fact that it takes a while for the Earth to heat up once it's received maximum insolation from the Earth, or from the sun rather. The sun has to heat up the Earth's surface, and then the Earth's surface has to distribute that heat to the atmosphere, and that takes a while. And so this lag of the maximum describes that lag between maximum insolation and maximum temperature. It's true throughout the course of a day, as we see here. It's also true, a very similar graph would appear throughout the course of a year. So the maximum insolation in the northern hemisphere would be on the summer solstice, but the maximum temperature for the northern hemisphere occur in late July and August, lag of the maximum. Finally, human conditions can affect temperature profiles, and one such investigated way is called the urban heat island effect. It has to do with the temperature profile around an urban area compared to the surrounding suburban and rural areas. So you can see here the urban area closer to the heart of the city has a higher temperature than the surrounding suburban areas and the surrounding rural areas. Why? Well, there's several reasons. Mainly, it's because of the building materials and the density of those materials in an urban center. So building materials, there's a lot of metal and different materials that are quick to absorb energy and heat up and store that heat and then slowly emit it over the course of the day. So even in the city it can be hot at night. As you know, if you've been to Phoenix in the summer, it never cools off there at night, or very minimally. Other reasons are the blacktop materials. We've replaced a lot of the natural ground with blacktop or concrete, which has very different properties than Earth has. It stores heat quicker, it heats up to higher temperatures, and it emits that energy throughout the course of the day. So this is called the urban heat island effect, and you can read more about it in the textbook. So be sure to read chapter 4 and do the labs that correspond to this chapter. Okay, talk to you soon. Bye-bye.